Okay, brilliant. So the title of today's talk is 5 Illusions that Challenge Our Understanding of Visual Experience. And what I'm going to do today is discuss 5 illusions that challenge the role that many supposedly fundamental processes make to our visual experience. So I'm going to try and take 5 different phenomena that claim to show that vision is an inferential process and show instead that these inferences don't appear to affect our visual experience. Instead, they merely appear to be inferences about our visual experience rather than affecting the visual experience itself. So that's the challenge I'm going to set today. Now, the emphasis is going to be on describing these illusions, right, rather than the data, which is something that I think, with the exception of the session today, we sort of lost as a community, right? If you think about Richard Gregory, he had a profound effect on the field by describing and exploring illusions rather than a focus necessarily on the experiments. And the key thing is all of the illusions you're going to see today are going to be at the demo night tonight. So please come down and check them out and tell me what you think. I put some red-blue glasses at the door, but actually, in effect, the lighting's not great for sort of stereo demos using anaglyph glasses, so we're going to skip those. But there is also a website, 5illusions.github.io, and a QR code that you can check throughout. Good. So, to kick off, what do I mean by visual experience, all right? So what differentiates visual experience from sound experiences, from touch experiences? Well, I think it's that we have an internal rendering, right? So when you see an object, your brain literally internally renders the front of the object, but not the back, right? And so what I want to get at is that process of internal rendering, which processes contribute and which processes do not. So let's start with color constancy, right? So this is a color constancy illusion. Those discs are the same on your retina, and then you see the one on the left, if I've got this right, is yellow, and the one on the right is blue, right? But does this really affect our visual experience, right? Is it like as if the brain is literally rendering yellow pixels on the left-hand side and blue pixels on the right-hand side, right? And the purpose of the first illusion, color constancy illusion, is to try and convince you that it's not affecting your visual experience, okay? So how are we going to do this? Well, if it really was affecting your visual experience, then as we alternate between the two conditions, right, what should you expect? You should expect to see a flickering, right, a phenomenal flickering between yellow and blue, yellow and blue, yellow and blue. By contrast, if it's merely a cognitive effect, right, then as you alternate between the two conditions, the appearance of the dish shouldn't change, and yet you should still be able to say, okay, it's yellow in this case and blue in that case. And this seems closer to our experience. So this is one of the illusions you can test today, right? So as you see, the appearance of the disk doesn't seem to change, right? And yet, I would argue, and you guys correct me, you can clearly be, let's give you another shot at that, yellow, blue, yellow, blue, yellow, blue, right? You can make those cognitive inferences despite the appearance not changing. Good. So if that's the right analysis, what we can say is that color constancy is a changing cognitive inference about a constant visual experience, right? So that's the first claim. Second illusion is size constancy, right? So these cars are the same size on your retina, and yet you see the far car is bigger and the near car is smaller. But again, the question is, does size constancy really affect your visual experience? And I want to be very specific about what this question entails, right? What we're asking is your visual experience of the image undistorted, or is your visual experience of the image distorted, right? And so a number of groups have gone on to argue that your visual experience of the image must be distorted, and that's the right way of explaining this size constancy effect. So Ni and colleagues and Hay and colleagues. But the purpose of the second illusion, the size constancy illusion, is to try and convince you that your internal rendering of the image, right, that your visual experience of the image is undistorted. Good. So let's take this image again and then put rectangles around them, right? Now, most people experience this as the cars still being pretty largely distorted in size. But the rectangles, by contrast, are minimally distorted or not distorted at all, okay? And why I think this poses a challenge is, if our visual experience of the image was distorted, then everything would have to be distorted along with the cars in the same way. And that just doesn't seem to be the case with the rectangles, right? And so again, what I want to say, size constancy is an inference you're making about your undistorted visual experience of the picture. The same I'd also argue applies to depth constancy. So as I take a separation in space and I move it forwards and backwards, right, the disparities are going to change massively on my retina. So as it comes close, they're going to be big, that's the blue. Further away, they're going to be smaller, that's the red. And so the assumption in the literature is there's a mechanism known as depth constancy that sort of counteracts this and ensures that you have a roughly constant percept of a separation in depth as it moves backwards and forwards. But again, and this is the purpose of the stereo illusion, I want to challenge whether that really goes to your visual experience, okay? And so in an illusion I showed last year at ECVP, you've got two conditions. You've got a back circle and a front circle in both conditions starting at a 10 centimeter separation. And the only difference between them is on the left-hand side, you're keeping the physical separation constant. On the right-hand side, you're reducing the physical separation that comes towards you in order to keep the disparities constant. And the question is simply, in which of these two conditions does it seem like the stimulus is moving rigidly and the separation seems constant? So you keep the physical separation constant, actually it doesn't look constant at all, right? You get a massive concertina ring effect. By contrast, you keep the disparities constant and everything looks nice and rigid, right? So there doesn't seem to be any evidence of depth constancy going on in our visual experience at the level of stereo. And to the extent it exists, it seems to be a more cognitive inference about our visual experience. I'll skip the anaglyph and we'll go into the fourth illusion. Because the strongest argument in favor for vision as an inferential process has always been the hollow face illusion, right? The suggestion that a mask pointing away from you actually looks like a mask pointing towards you, okay? And that's what I want to question. So does the hollow face illusion really invert 3D depth from stereo vision? Do we literally see an inverted 3D world? And the question I want to ask is what happens when we put objects into the hollow of the hollow face, right? Now, if everything was inverted, we'd expect to see the objects behind the hollow face, right? A complete inversion in depth, okay? But that's not what we see. Instead, we see two things. So first, we still see the hollow face illusion as evidenced by the motion of the face. So that's a key criterion. But second, and this is a key thing, we perceive the veridical stereo depth between the objects and the face, right? So stereo depth is not inverted despite the hollow face illusion functioning. So if you come down to demo night tonight, I'll show you this stimulus, right? You'll see the hollow face illusion in stereo, and you will see the veridical stereo depth between the first set of bars, the second set of bars, and the tip of the nose. And we'll skip the anaglyph. There's also another version of this illusion, the morphing face illusion, right? So what you do here is you put points on the base and the tip of the nose, and you flip back and forth, right? You alternate between a protruding and receding face. And as you do that, you experience two things. One, you always experience the hollow face illusion. Again, that's the test we need to see. But second, and most importantly, you actually see the change in relative stereo depth as the points go back and forth, right? So that's crucial. So in sum, I argue that both of these demonstrations show that despite having the hollow face illusion, it doesn't invert stereo depth. This isn't sort of Q integration giving you a single coherent percept. Good. Now for the final illusion, visual scale. And the question here is, do we literally perceive objects as being near and far, right? So that's one way of thinking about size and distance perception. Or should we think of size and distance perception in the real world, more like watching television, right? Where you judge what you're seeing as either big or small, without the object literally having to be perceived as closer or further away from you, right? So it's real-world distance perception, a lot more like the television case. The case I want to think about is Helmholtz's telestereoscope, right? Where you increase the separation between the eyes and the world seems miniature. But does this telestereoscope really make far objects look near, right? That's the essential question. Now, the traditional argument in literature is, yes, we've got all these triangulation cues. We've got vergence, the angular rotation of the eyes. We've got vertical disparities, the vertical offset of points, changing the perceived distance of the object, right? By contrast, what I want to explore is the idea that actually this whole effect is due to horizontal disparities, changing the perceived 3D shape or geometry of the scene, but crucially, it's not changing the perceived distance of the scene and its objects, right, from the observer. Good. So this leads to the scale illusion, which is in virtual reality, and it alternates between two conditions. So condition one is the Helmholtz condition, right, where everything, vergence, vertical disparities, horizontal disparities are closer than normal, and as predicted by Helmholtz, everything looks nice and miniature. By contrast, the second condition, although it sets vergence and vertical disparities as closer than normal, it sets horizontal disparities to normal, right? And we observe two interesting things as we alternate between these two conditions. So the first thing is this second condition looks normal, right? Not small. So that's a really good indication that the whole miniaturization effect was actually due to these horizontal disparities, not vergence and vertical disparities. But second and more startling is how the change in scale occurs. And come down to demo night and see if you experience it for yourselves, right? As we toggle between the two conditions, the change in scale isn't about the scene shifting towards you or shifting away, making it seem smaller or further away. Instead, the change is in the distortion of the 3D shape of the scene relative to the observer. Good. So in this sense, visual scale really does seem closer to the television case than we traditionally thought, right? There's no sense in which seeing an object as larger or smaller in the real world, if this is the right analysis, literally depends on seeing things as closer and further away. As I said, come down to demo night, give it a try, see what you think. But in conclusion, what we've done today is discuss 5 illusions that challenge the role that many supposedly fundamental processes make to our visual experience. And I would argue that taken together, they suggest that visual experience is much simpler than we previously thought. So do check out the website with the discussions of the illusion, and all that's left is to say thank you to the Gnomes Foundation and to the Krieger-Skorte Lab. Thank you.